So today we're going to be covering proximity probes and other vibration sensors. Vibration transducers basically convert motion into millivolts. For displacement, it's mils of displacement to millivolts of electricity. Generally, we have two types of bearings. You have your roller element type bearing and your fluid film bearing. And we monitor these generally quite differently because of the physics of each one. For the roller element bearing, you have a very physical link between the shaft and the casing in the roller elements. And the shaft does not move very much relative to the bearing or the bearing housing because of that very direct physical link. So using a proximity probe mounted to the bearing face or to the bearing cap would not show very much motion because it is very limited by the available clearance between the elements of the bearing. However, it does transfer energy very well from the motion of the shaft into the casing of the machine. And as long as you mount a case mounted sensor near that bearing cap, you can get good transmission of that vibration data to that sensor. However, on a fluid film bearing, the fluid acts as a cushion and absorbs the motion or energy of the shaft motion and does not transfer it as well to the casing. So therefore, using a proximity probe that is mounted to the bearing face or to the bearing cap, looking at the shaft, you do get a view of the motion of the shaft relative to where it's mounted. On very large mass rotors, or where the mass of the rotating component is a higher ratio to the casing mass, you can get pertinent data from mounting a case-mounted sensor on the exterior of the bearing. Quite often you see that with nuclear steam turbines. They will have a velometer mounted in the same plane as the proximity probe. And so with that, we can get the motion of the shaft relative to the mounting point, the motion of the machine case relative to a point in free space. And by summing the two, we can get the motion of the shaft relative to a point in free space. So you can get a lot more information. We also see where mounting transducers on the outside of a fluid film bearing are good for detecting things like foundation issues, also where there are outside influences that may shake the casing. On one side I was at, they were taking down the stacks at a power plant to go to a scrubber type system, and they put velometers in a number of places on the machine and on the foundation to measure and compensate for the dropping of those stacks, and it basically just created an earthquake type effect. And you could see that stack drop, and everything would kind of go haywire for a bit and then settle back down. And by having that motion of the casing to correlate with the proximity probes, we were able to tell if we wiped a bearing or anything due to that impact. So we're going to start with proximity probes. Proximity probes measure displacement. Generally used with fluid film bearings. It is capable of going down to low frequency actually 0 hertz, because things that aren't moving can be measured in displacement, or not rotating, can be measured for displacement. Things like case expansion, thrust, differential expansion, things like that that do not require rotation gets down to the 0 hertz. And it's generally reported here in the States in thousandths of an inch or mils, and in other parts of the world they use microns. It is generally built up of 3 components: the proximeter, the extension cable, and the probe. These are series specific, so the 5 and 8 millimeter proximity probes, the probe, cable, and proximeter are all color coded. You can see they have the blue here, and you have a blue label on the proximeter. At the end, I think I've got one that's got a purple set, which I believe is the 25 millimeter. But by looking at it, you can visually confirm that they are the correct ones for that series. They do need to be matched as an electrical length. So the proximeters for the 8 millimeter probes come in either 5 meter or 9 meter without any kind of modification. And that means that the total length of the extension cable and the probe electrically, not necessarily physically, sums up to that 5 meter or 9 meter. So if you have a 5 meter proximeter, you want either a 4 meter extension cable and a 1 meter probe, or a 4.5 meter extension cable and a 0.5 meter probe. Same thing goes for your 9 meter. As long as the total of the extension cable and the probe add up to the total length of the proximeter, you should be okay. Now, how do they work? The proximeter produces a oscillating signal at a radio frequency, and as that passes through the probe tip, which is basically wound as an antenna, it generates a field around the tip, and as a conductive material moves into that field, it generates eddy currents in the surface of the material, and that creates a loading on the signal. And by reading that loading and unloading, we are able to measure the displacement. So the very fast squiggly line here is the radio frequency oscillation from the proximeter. As the material moves in and out of the range of the proximity probe, as it moves further away, we have less or full signal. As it moves into the field, it absorbs that energy as a eddy current. So again, here we're showing it as a demodulated signal. So we remove the radio frequency component of it, and we are looking at just the waveform that is left as it moves in and out of the field. So here, the probe is far away from the shaft material. With a 8 millimeter proximeter, you're generally going to see something in the 19 to 21 volts negative. If there is no material in the field, and as you get closer, oops, wrong way, and the shaft gets right up against the probe tip, you'll see it go down to about a negative 0.65. There is a dead band of about 10 thousandths of an inch from the probe tip before it starts to change. So generally have to get about 10 thousandths away from that probe tip before you start seeing the voltage go more negative from that 0.65 volts. So once we extract that demodulated waveform, we measure generally peak to peak for your peak to peak vibration. So measuring from the lowest point to the highest point, we get your peak to peak. We can also do peak, RMS, other values can be calculated from that waveform. And the DC gap voltage is the average value of that waveform. So the DC gap gives us basically the distance the shaft is from the probe tip, and the AC component is the vibration movement. We do both radial and axial measurements with proximity probes. Quite often everybody's familiar with the XY vibration component of using prox probes on a fluid film bearing. One thing that many people don't pay a lot of attention to is that DC component can also be used to measure the position of the shaft in the clearance of the bearing. In System 1, we plotted as a shaft centerline plot, and if it is a horizontal machine and lift oil is off and the machine's not rotating, the shaft should be sitting at the very bottom of the bearing. You can save that as a reference point and put in the clearances of the bearing in the shaft centerline plot and be able to see that you do get lift when you turn on lift oil. If you have a restriction to the oil flow and you don't get lift, it can definitely save a bearing from being spun up dry. You also can see as the machine comes up to speed, you see the oil wedge build and push the rotor to the side. And if you do have a machine incidence and it does wipe a bearing, you can actually go in and look at that shaft centerline plot and confirm that the bearing was wiped. We also measure axial movement, looking at thrust, differential expansion, rotor expansion, and case expansion. Case expansion is not a very common use for proximity probes. Usually it's a greater distance than the proximity probes can properly read, so often that's used with an LVDT. These signals can also be read as vibration. I have run into cases where there was axial vibration in a machine and we just jumpered the thrust probes over to a radial vibration channel pair and were able to see how much axial vibration they were getting and help them diagnose what was going on. Proximity probes can be landed up to 4 times on different instruments without getting into serious loading. Accelerometers, velometers, generally, if they get connected to more than one monitoring source, it does load the signal and degrade the quality. But proximity probes can be, depending on the electrical components, can be connected up to 4 times. We also use proximity probes as a Keyphasor. This gives us a once per revolution marker point, and having that marker point recorded and the angle at which the probe is installed and the angles at which the X and Y probes are installed is necessary for doing proper diagnostics and also for doing proper balancing. We usually use a notch because a notch is the easiest one to deal with. You have the greatest chance of gapping the probe against a surface that is appropriate without having to get in there and actually look for the physical notch being not lined up with the proximity probe. I have had numerous cases where just pure bad luck, they did get the probe lined up with the notch, gapped it, but they gapped it at the bottom of the notch, and as soon as they started the machine up, it broke the tip off the probe, and it was required replacement. With a projection, you do have to make sure that you roll the rotor to the point that the projection is under the tip of the probe. And if the projection is something like a key in a keyway, for larger shafts, you do need to make sure that the corners are rounded down on that outer surface so that when you gap that probe in the center of the key, as soon as that starts to turn, those square edges of the key are physically further out from the center line of the shaft than that center mark of the key is. And you can either get into having a double pulse or actually physically breaking the tip again. For thrust, we recommend that you install the probes within 12 inches of the thrust collar. Best practice is to have it actually on the thrust collar, but some cases that is just physically not possible. But as long as you get it within 12 inches, generally we don't run into a problem. However, if you put it further away, say on the other end of the shaft, you can get into thermal expansion issues. And if you're fighting how the rotor's thermally expanding versus actual thrust movement, it really makes it hard to comprehend what's actually going on with the thrust. I've got to kick out of display mode to go through this section, so just a second. One of the things that I quite often get asked is about the gapping of proximity probes. Customers will call up and go, hey, I've got this machine that the probes are gapped perfectly at -10 volts right in the center of the linear range. And I've got this other machine over here that's gapped at -6 volts. Is that throwing my vibration reading off? And the answer to that is no, not unless your vibration reading is massive. So here we're looking at a 10 mil peak to peak, which is for a 8 millimeter probe about 2 volts at 200 millivolts per mil. So at a -10 volt average, we only have a 1 volt less negative and 1 volt more negative swing. So we have a great deal of room to both the upper and lower OK limits. The upper limit for a 8 millimeter proximity probe is about -1.6, and the lower limit is about -16. So as long as I do not cross over into that not okay range, the probe will read accurately, as long as the system is matched length and for material. So here, if my OK limit is at negative 1.6, and we only have a 1 volt difference to the center line. As long as I'm over 2.6 or over negative 2.6, I'm not going to get into that OK limit. So you can have a very wide range of gap setting and not run into issue. However, we do recommend that you set it in the middle of the range to give you the greatest amount of clearance and available room possible. Machines with quite large clearances, when you gap that probe, they're generally gapped or come in from the top. So your shaft sitting down at the bottom, you've got your lift oil, you have your oil wedge, all of those are going to lift that shaft up. So even if you gap it at a perfect negative 10 volts when the machine isn't running, it's not going to be a perfect negative 10 volts when the machine is running. I'm going to switch back to the presentation view. Now, we do recommend that you run a calibration on your proximity probes once a year. We also realize that you guys are in the process of, or in the business of making money, and to make money, you got to have the machines running, and you're not going to take them down every year just to check the proximity probes. So we do recommend that you check them anytime that you have access to the probes. To check them, you take the probe out of the machine, you put it into a spindle micrometer cradle, and you basically set your spindle micrometer to 0. You butt your probe up against the spindle micrometer target and lock it down. The target does need to match the material of the shaft. And then you have a meter connected to the proximeter looking at the gap voltage or the DC voltage. And you record that as you roll the spindle micrometer out. So every 10,000 or every 10 mils, you will record the gap voltage. And our guys use a Excel spreadsheet that's set up to graph and give you a nice linear system if everything is functioning as expected. And we also have it where it calculates the average scale factor for a 8mm probe. Should be in the 200 millivolt range per mil, but the specification allows for 188 millivolts per mil to 212 millivolts per mil. Most of the time I've seen them in the 195 to 205 range, which is within spec. You can get very strong changes in your signal if you have the improper cable length. So if you have a 5-meter proximeter and you have a 8-meter extension cable and a 1-meter probe for a 9-meter cable length, you will get a long setup, and that will read much less vibration than is actually occurring. If you have a short system where you say have a 9-meter proximeter and you have a 8-meter extension cable and a 0.5-meter probe for a total system length of 8.5 meters, you will get more vibration being reported than is actually occurring. So something very important to check, and the longer the system, the more important it becomes. We have a mod for the 8mm probes to allow up to a 13-meter length, and we had a customer that used that mod, and they ended up with a 12.5 meter system. So they got a 12-meter extension cable and a 0.5 meter probe. They should have installed a 1-meter probe. And there was a 30+% difference from actual vibration to what was being reported. And since it was short, it was reporting 30% higher vibration than the machine was actually showing. Also, your target material has a big effect on the linearity and the scale of the signal. Our standard proximeter is calibrated for 4140 stainless steel. Any other alloy of stainless, any other material, any plating material, anything like that, you need to change the calibration of the proximeter. I think the last time I looked, we had somewhere around 240 different calibration mods that could be applied to proximeters. Pumps are probably one of the most common places that I see where they change the shaft material on a regular basis due to them trying to fight corrosion. So anytime you replace the shaft, make sure that you confirm what the shaft material is and get a proximeter to match. It can throw the signal off a good bit by scale, and in certain alloys, it actually causes kind of an S-type shape to the curve, so it's not even linear. So you can't just say, oh, well, it's a 165 millivolts per mil. So making sure that the proximeter is calibrated for the shaft material is very important. Some of the common pitfalls, crosstalk. If you get two probe tips too close together, the radio fields can interfere with each other, and that causes false signals. If you're measuring a small shaft and having the two probes 90 degrees apart, or if you have a Keyphasor in the same area, you may need to shift one probe axially along the rotor to just prevent the two from interfering with each other. Generally, you want to have at least 2 to 2.5 times the probe tip diameter between the center lines of the probes. So if you're talking about a 8mm proximeter, you want at least 20 millimeters between center lines. Another issue you run into is what we call side view. This is where that radio field picks up material from the side. On installations, we recommend that you have a relief cut near the shaft if the casing comes near to the shaft. That is that 2.5 times the diameter of the tip. And you can actually get to a negative 10 volt gap setting by side view. So one of the things that you need to do is make sure that the probe actually gets down to the shaft and is looking at the shaft, not looking at casing material. One of the ways you can do that is to use a plastic, copper, or bronze rod, insert it into the hole, see where the shaft is, measure that on the probe, put yourself a little mark, and then roll it in to that to no more than that depth. Also, monitoring the DC component of the signal from the proximeter with a meter, rolling it down to a -2 volts. You can't get to -2 volts with side view. So if you get to -2 volts, you know that you're looking at the shaft, and then you can back it out to your -10. One other thing that I've seen people do is run the probe all the way down till it touches the shaft, feeling for that extra tightness as they roll it down. And that can lead to cracking of the tip, and which damages the antenna, allows oil ingression, things like that that just destroy the probe. So again, we recommend you just roll it down to a -2 volts and then back it out to your proper gap setting. You also need to make sure that you have an appropriate target size. If the radio field is wrapping around the sides, it will not read accurately. So we have a minimum shaft diameter and also a minimum flat target size. You do also need to make sure that that flat target is available all the way around the circumference. I had a customer that was retrofitting thrust probes on a machine. They found a nice flat machine surface and they built their bracket, but what they didn't think about was that machine surface was over the bolt holes for the coupling, and as soon as they rotated a couple degrees, a bolt hole passed under what was supposed to be a thrust reading, thus invalidating the thrust. So they had to relocate it to a different spot. It was just one of those didn't think about the machine actually rotated moments. Proximity probes for radial vibration generally get installed in two methods. One is an internal and the other is an external mounting. Internal mounting is usually inside the casing and uses some sort of bracket to hold the probe to the bearing cap or the bearing face. Having the cable tagged down every 12 to 18 inches does keep the cable from flopping around, getting physical wear, and also picking up stray current and inducing a electrical signal that is not vibration and giving you an erroneous signal. So making sure that those are tagged down can be very important. Generally, it comes out through some sort of oil seal and into a junction box. If you are running into an issue where you have oil wicking through the cable, say you have a positive pressure casing, if you start getting oil in your junction box, we have a fluid lock cable that has silicone injected every 6 to 12 inches to act as an oil dam to keep that oil from wicking back up the insulation of the cable. So if you have that problem, switching to the fluid lock cable should eliminate that for you. Couple issues, considerations for doing the brackets. You don't want it to be more than 6 inches from the face or from the bearing. You want to use at least 2 bolts to keep the bracket from rotating. You also want to make sure that the bracket will not resonate or vibrate due to any condition in the machine. Doing a resonance study, design review of the bracket, just to make sure that it's not going to cause you any issues and have to open a machine up to either replace or reinforce a bracket. That can get a bit more tricky if you have redundant probes and or have the shaft absolute set up where you may have a velometer on the same bracket as the proximity probe, and you just don't want to have that flexing or moving around. So the next method is the external mounting, where the probe is basically mounted through the housing using a a housing. So mounted through the casing using a housing. Generally, it's a 3/4 pipe thread that is cut into the machine case. This portion here is the lower housing. This is a stinger that goes through. The probe in the stinger is replaceable. It's just a reverse mount probe. And you've got about 2 inches of thread in here to gap the probe. And if we have the measurement from the outside of the machine case to the shaft, we can pre-cut and thread that stinger for you. Or if you want, we can supply you with a long stinger that can be cut and then internal threads tapped into the bottom of the stinger to mount the reverse mount probe. We offer 2 varieties or 2 styles. The 31,000, 32,000 is a composite housing. It is API 670 compliant. And then we have the explosion proof in a 21,000, which is aluminum, and the 24,701, which is a stainless steel. Field wiring, with standard wiring, we have a 1,000-foot limit. That is with 18 gauge wire in a non-hazardous environment and looking at a frequency range in the 0 to 10,000 hertz, because all of these things affect how the signal degrades through the cable. You can go over 1,000 feet, but we do need to do some calculations with the frequency, hazardous areas classification. Using things like barriers can actually increase the available usable cable length, and going to a better capacitance cable can also extend that range. So we've got a calculator. So if you need to go greater than 1,000 feet from the proximeter to the monitoring system, get in touch with us and we can help you sort out what kind of cable you need to source to do that. So here, again, I mentioned at the first that we had the blue bits. Here we've got the purple bits. So this is a different setup. And so I believe this is either the 11 or 25 millimeter. I can't remember what purple is. So proximeter, probe, and cable would all need to match. We offer a 5 millimeter, 8 millimeter, 11 millimeter, 25 millimeter, and 50 millimeter tip sizes. We also have it available in a ceramic capped for corrosive environments. We have the narrow side view version, which we discussed in the Pitfalls. We offer a radiation resistant variant. We also have the fluid lock available, and we also have a underwater series of probes that have greater water ingression resistance. One of the questions that comes up quite often is the 3300 versus the 3300 XL. If you see the gold connector on the cable, that is the 3300 XL. The 3300s had a silver connector. The 3300 8 millimeter is compatible with the 3300 XL systems. So if you have a 3300 probe, a 3300 XL extension cable, and a 3300 proximeter, the system will work just fine. So the components are interchangeable, but the 3300 XL has the gold-plated connectors that have click lock. With the 3300, you had to go finger tight on the connector and then another quarter turn with pliers. The 3300 XL has the click lock, so it has a ratcheting self-lock to keep it from loosening over time. The 3300 had a center core, the insulator, a shield, which was the negative, and then just a outer jacket. The 3300 XL increases that protection to having a dual jacket, another metal mesh shield, and then an outer jacket. This helps with abrasion resistance and RF. So the 3300 XLs are much less susceptible to noise and damage. All right, we're going to stop there for any questions on proximity systems.
Okay, here's the top one. 5mm and 8mm probes shouldn't be gapped at -9 volts.
They can entirely be gapped at -9 volts, as long as you are in the, depends on what your expected full scale range is, but generally most machines aren't going over a 0 to 10 scale range. So as long as you're in that -2.6 to 15 or -15 volts, you're going to get a signal that is perfectly fine and representative of the motion inside the machine.
Okay. This next question I replied to, but I may as well go over it. And that is, when do you use a multi-event Keyphasor versus a single-notch Keyphasor? And what sort of data can we get from a multi-event Keyphasor versus a single-notch? So we have a multi-event wheel that we use on recips that has 12 notches, and in between one of those notches is a double notch. And we set that double notch so that it corresponds with top dead center of the first throw of the recip. As you can imagine, recips have some torsional issues, and the speed during one revolution of the shaft is not constant. So we use those 12 notches to tell us what the timing is. For a single event Keyphasor, we recommend those for all centrifugal compressors or machines, and they give us that once per turn phase reference that we use for balancing and understanding where resonances are and so forth. So that's the answer there. I'm going to give you one last one and then we'll move on. And it is, in an event where sensors are paired with different than adequate wire length, is there a way to estimate or calculate the corrected vibration readings? So he's saying, if you have a mismatched
system,
set of extension probes or extension cables and probes.
The only way to accurately calculate it is to physically pull it out or set up a similar system on the bench and do a linearity curve, like we talked about, where you put the probe in the bracket and measure every 10 thousandths or 10 mils and see what that comes out to.
Okay, sounds fair. We'll answer the rest of the questions at the end of the session. Thank you.
Okay. So now we're going to move into case-mounted or seismic transducers. These break down into basically 3 categories. You have velometers, accelerometers, and velocity pickups. Velometers and accelerometers are basically the same physical components. The velometer generally just includes a conditioning, integration, and gain circuit to do the integration from acceleration to velocity. You want to do that integration on board because the math of integration greatly exaggerates low frequency signals and reduces the influence of higher frequency signals. And so any low frequency noise that gets induced in the cable going back gets exaggerated. So doing it on board reduces the chances of getting noise. Velocity pickups are the spring, coil, and magnet type. They are self-generating. They supply their own power. Basically works on the principle of a magnet moving through a coil of wire generates an electric current. By using that, having that coil of wire on a set of springs around a permanently mounted magnet, as that machine vibrates, the inertia of the coil causes it to oscillate around the magnet, and we measure that current and calculate the velocity of the vibration from that. Upsides are that it is a self-powering unit and it is very good for low frequencies. Some of the downsides are it has moving components, so they do fatigue and wear. So we do recommend that you do a verification of those sensors a little more often than you would a piezoelectric. Verification basically consists of putting it on a shaker table and inputting a specific vibration level and making sure that the velocity pickup is outputting the same value. Another downside is these are quite often orientation limited. So if you buy a 90-degree plus minus 10-degree sensor, you have to mount that plus or minus 10 degrees from 90 degrees. With the piezoelectrics, they don't have the springs, so they don't care at what orientation they're mounted. That orientation basically relates to how the springs are set up inside the velocity pickup to support that coil so that it doesn't touch the magnet and the coil moves freely and gives an accurate reading. The piezoelectric style consists of a reference mass, a preload bolt, a piezoelectric crystal, and a charge circuit to pre-charge the piezoelectric crystal. And as the machine moves, that reference mass, the inertia of that reference mass compresses and relieves the pressure on the piezoelectric crystal, causing it to give a electrical signal that we then convert into the inches per second. Accelerometers, basically the same thing, just doesn't have the integration circuit. Here you can see the reference mass. The piezoelectric crystal is actually up here in the top. Accelerometers are better for measuring higher frequencies, quite often used around roller element bearings, internal gear mesh measurements, can go up to 20,000 hertz. As you get higher in frequency, the reference mass has to go down due to the inertia of the reference mass. Getting a 20-pound weight to change direction 20,000 times a second is nearly impossible. The amount of energy required is monstrous, but getting a gram or less of mass to change direction 20,000 times a second takes much less energy. So for something like a earthquake sensor, having a large mass where there is a lot of energy moving very slowly makes sense. Having a small mass at high frequency makes sense. So making sure that you're using the right size inertia mass to get the appropriate frequency range that you're needing to monitor is important. And they generally output in inches per second squared or Gs. You'll see two styles of accelerometer out in the world. The most common is the compression type. Uses a preload bolt to hold an inertia mass against the piezoelectric crystal. The issue you run into is around thermal expansion. All of these components have a different rate of thermal expansion. So under high heat or where there is a large thermal cycle going from cold to hot, hot to cold, that difference in the thermal expansion of each material can cause what we call stack slip. And as that sensor heats up, you'll see these spikes of 80 or greater Gs, and has nothing to do with the vibration of the machine. It's just that thermal growth of all of these components. To get around that, here more recently, they have come out with the shear type sensor, which uses a piezoelectric element with a reference mass out on the end, and there is no preload bolt. This is hung out in free space, and as that reference mass moves up and down due to inertia, it flexes this piezoelectric core, and we read that current from that core. Not having a stack of items makes it much less thermally sensitive. So these we see going out to 900 degrees F or so, where generally these are limited to 350 to 400 degrees F. So accelerometers generally have the widest usable frequency range. Higher frequencies are kind of its sweet spot. Piezoelectric velocity sensors have a smaller useful frequency range, but are better down at the lower frequencies. Moving coil, again, lower frequency, and also does not have a need for an external power supply. Some of the requirements and pitfalls, spot facing drill and tap is the most recommended method of mounting. Some sensors do have a pipe thread so that they don't need a spot face, but you still have to drill and tap. We also see epoxy mounts and mag mounts a good bit. Making sure that you use an epoxy that gives you good transmission of the vibration, a good rigid epoxy. If it's a softer, gummier epoxy, it can actually damp your vibration. Mag mounts, I've seen some setups where it's quite a stack of components between the magnet and the adapter plate to adapt the magnet to the sensor, and then the extension cable and everything, and it can get 6-7 inches. You just have to be careful and make sure that you're not getting motion of the sensor that is not related to the actual motion of the machine. Nothing's dragging it down. Most of these sensors have a very small torque installation spec. It's generally in the inch-pounds of torque for installing these. Having somebody out there with a large wrench twisting these down, getting them really tight, tends to shatter the crystal inside. So whenever you're installing these, take a look at the data sheet, find out what the torque setting is, use a torque wrench, and install them properly, just to keep from damaging the sensors. You also want to either label them or protect them so that people don't use them as handholds or footholds to climb up on the machine. Again, that torque issue where you can crack the crystals or damage the sensor or get it out of orientation with the machine because they bend it. Last thing we're going to talk about is transmitters. These are basically the same things that we've been talking about, but they have an extra circuit in there to convert a specific range to a 4 to 20 milliamp output. With that 4 to 20, you are only going to get the overall amplitude, which is great for watching it through a DCS or a PLC just for condition monitoring. All of them do still have the dynamic data available on the system. So you can use a Adre or portable data collector to go out and collect all this other great data that is useful for doing diagnostics. For radial vibration with proximity probe, we have the 990 series. There are a number of scale ranges for the 4 to 20 milliamp scaling. Same thing for thrust with the 991. These do require an active 4 to 20 milliamp circuit. So you have to supply the power. That powers up the proximeter and powers your current loop. And here on the 990, 991, you have the common and prox out for reading the dynamic signal. There's also a BNC connector that you can connect to with your portable data collector. The 177-230 gives you inches per second. We offer 3 different scale ranges. Again, it is an active loop power, so you have to supply the voltage. And it does have the dynamic signal just between the C and B pins will give you the dynamic signal. Here we've got a picture of one of the shear mode type transducers. Generally, the piezoelectric component is housed separately, and then they use a mineral insulated hardline cable to go back to the electronics, just to get the electronics out of that high temperature so that they have a chance of surviving. Where this head might survive at 900 degrees plus, these electronics really need something under the 300 degree type range. We do offer a protective housing. So once the sensor is mounted to the machine, you can have the 3 holes drilled and tapped around it and place this housing over it. There is a gasket to keep out oil, debris, other things, and gives you a protection from environment and from damage from people and other objects. So we do offer a spacer. So if you have a taller sensor or a tall connector on there, you can insert a spacer to get clearance for that. So we do offer our standard accelerometers, high temp accelerometers, and also low power accelerometers. Velomitors, standard, low frequency, hypertemperature, environmentally hardened, and radiation resistant. One thing I do want to mention is there are positive voltage sensors and negative voltage sensors. The positive voltage sensors will work with a negative voltage system, and the negative voltage sensors will work with a positive voltage system, but the signal will be 180 degrees out of phase. So you need to be aware of the polarity of your signal, and you can build a small electronic circuit to invert that polarity if needed. So I guess we are down to questions.